Okay, so today we're going to look at uncertainty calculations and how they could ask you sort of exam questions on it and how you can put them together. So whilst carrying out practicals, as part of your CPACs, you should have been sort of selecting instruments that give you the lowest uncertainty or lowest percentage error, and you should be sort of accustomed to being able to calculate uncertainties of measurements. Just remember that there are two general classes of things. There are implements where you just take one judgment, and there are implements where you take two judgments, and we'll see in a minute how that affects calculating the sort of uncertainty of each measurement. So remember when you're taking a measurement, for example with a thermometer, if you've got 1 degree C intervals, the uncertainty is half of each division. Often they are written like this, so you have your measurement plus or minus the uncertainty of the measurement with the units after. Remember, for measurements, not readings, you've got two uncertainties that you need to include. So when measuring with a ruler, so here we've got our object, you line up one end of the ruler, you line up the other end of the ruler, and you're making a judgment about whether each end has lined perfectly with your object. So you have to double your uncertainty of measurements because you're taking two measurements. So in this case with the ruler, you'd have your divisions are 1 millimetre, so you'd have 0.5 millimetre uncertainty there, 0.5 millimetre uncertainty there, so the total uncertainty for that ruler would be plus or minus 1 millimetre. Okay, so here are two examples of implements where you take readings. We've got a measuring cylinder and we've got a pipette. If you could please try and work out what the uncertainty of each measurement would be, pause the video and then I'll reveal the answer. So the uncertainty of the measuring cylinder would be 0.5 centimetres cubed. So each division was 1 centimetre cubed, and you just need to read the one measurement, so the one reading from where the solution will go up to, and half of the division is 0.5. For the pipette, the uncertainty is 0.05. Yes, we've got each line going up in 1 centimetre cubed, but each has got 10 divisions. So that would be 0.1 centimetres cubed, and half of that would be 0.05. And again, it's a reading because you're just making the judgment, but where the bottom of the meniscus goes up to. So pipettes are often more precise than measuring cylinders with a lower uncertainty. So here we've got a ruler, we've got a measurement. Can you just have a go at this question? Pause the video, and then I'll reveal the answer. So you can see here, again we've got millimetre divisions, so half of that would be 0.5 millimetres, but you're taking two readings, so it's a measurement, so you double it, so it would be so that's actually incorrect, that should be 1.0 millimetres for the uncertainty. Okay, so for percentage uncertainties then, so rather than just the uncertainty of each measurement, you do the uncertainty, so that might be like plus or minus 1 millimetre or plus or minus 0.5 centimetres cubed, something like that, divided by the value times by 100. For means, you just divide by the mean value, don't need to do anything fancy with it. So could you have a go at these three questions here to work out percentage error or the percentage uncertainty? Pause the video and then have a go. So you can see here that these are the answers for these three. So we've got the uncertainty divided by the measurement times by 100 in each case. So in an exam they might ask you to sort of combine uncertainties together, and this is where it tends to get a little bit complicated. So if your equation you're adding together, adding or subtracting values, then you add your uncertainties together. So for example, this leaf has, what's the difference in length of this leaf? Well, each has got an uncertainty of 0.1 centimetres. So the leaf has grown by 2.2 centimetres. But to get the uncertainty, the percentage uncertainty, you add each of those raw uncertainties together. So you add those two 0.1s, and it gives you the absolute uncertainty of that measurement. Sorry, not a percentage uncertainty, an absolute uncertainty for that difference in length. Another example here, this could be done with micrometers, so measuring using an eyepiece graticule or something like that. So you're looking at a root or root hair, and it's grown. It's gone from 3.4 to 8.5 micrometers. So here we go. So the difference, the growth would be 5.1, and then you're adding the two uncertainties together to get plus or minus 1.0. So the next type of percentage uncertainty is if you're multiplying values together. So often they might have a rectangle as representing a cell. You might have to work out the area of that cell and then work out the percentage uncertainty of those measurements. So what you do with these is you simply add together the percentage uncertainties. So not the raw uncertainties of each measurement, the percentage uncertainties of each measurement. So in a rectangle example, the area of a rectangle is length times by height, or width times by length, whichever way you want to do it. So in this example here, we've got a length of 12.4, and we've got a height of 8.5, and we've got the uncertainty of each of those measurements. So to get the percentage uncertainty of a length, remember you do the uncertainty divided by the measurement times by 100. So this comes out with 4.84, 0.6 divided by 12.4 times 100. And the uncertainty of height would be 0.4 divided by 8.5 times 100, giving 4.71. So the area of the rectangle is your length times your height, and the total percentage uncertainty, you add the two together, and it gives you 9.55%. Okay, this one's a bit more complicated, so please bear with on this one. So when dividing values, one example you might use this is in the magnification calculation. So the actual size is equal to the image divided by magnification. In this example, we're going to say the magnification is 5,000, and we're assuming there's no uncertainty with this. The image, or the width of this cell, was measured to be 20 millimeters, plus or minus 1 millimeter. So we used a millimeter ruler to do that. So, to get our actual size, it's image divided by magnification. So to get the uncertainty of the actual size measurement, you'd do the same. So you have the image size uncertainty, which was 1 millimeter, but we want our final answer in micrometers. So that'd be 1,000 micrometers divided by magnification, which was 5,000, and that gives us 0.5 micrometers. So that's the uncertainty of our actual size. Our actual size was 20,000. Remember, you've got 20 millimeters times by 1,000, so it's 20,000 micrometers divided by our magnification is equal to 4 plus or minus 0.5 micrometers. So that's an important thing to do. That's not using this. That's an important step that you need to know how to use. So then how do we use this percentage uncertainty of our measurement, total percentage uncertainty for this calculation? Well, the uncertainty of the actual size, percentage uncertainty for the actual size, remember, is measurement. Uncertainty divided by measurement times by 100. So uncertainty divided by measurement, uncertainty divided by measurement times 100 is 12.5%. Now put that into this equation. You add your two percentage uncertainties for each measurement together. So it's 12.5% plus, we've got a 0 here because we assumed there was no uncertainty for magnification. And that gives us a total percentage uncertainty for the actual size of being 12.5%. So this is the fourth and final example of uncertainties, percentage uncertainties, and how to combine calculation together. So in this one we've got the power rule. So to work out the percentage uncertainty of this, you do the power times by the percentage uncertainty of that measurement. Common way they might approach this is if you've got, assuming a cell is a sphere, and then working out the volume and the percentage uncertainty of that volume. So in this example we've got a cell with a radius of 20, that should be micrometers, so 20 plus or minus 1 micrometer. So volume of a sphere is 4 over 3 pi r cubed, which gives us 33,510 centimetres cubed. So the percentage uncertainty of the radius, remember it's uncertainty divided by measurement times 100. So uncertainty 1 divided by measurement 20 times 100 is 5%. So if that's the percentage uncertainty of the radius, what's the percentage uncertainty of the volume? So it's power times by the percentage uncertainty of the measurement. So it's 3, because that's the power, you're cubing the radius, times by the percentage uncertainty of that measurement is 5, so that gives us 15%.